Hello everybody, we enter week 2 of this course. In the first lecture of this week, we shall have a quick recap of what we discussed in week 1. Then we shall discuss various representations of basic logic gates. We shall also discuss universality of NOR and NAND gates, its usefulness and also usefulness of AND or invert gate. If we recollect, in brief, we had a look at in week 1 of following concepts. Manipulation of digital signal is fundamental to digital technology. Switching and logic operations are key at hardware level implementation of digital technology. Transistor based circuits are important for realization of this switching and logic operations, because we get inverting operation through transistors. TTL and CMOS based logic gates have wide applications as building blocks of digital electronic circuits. And you also remember that there are practical issues like propagation delay, noise margin, fan out, power dissipation, so on and so forth, which need consideration when we develop digital circuits or complex digital building blocks. To start with, we recollect that we had discussed inverter through CMOS technology, through TTL technology, and we have given a circuit of the inverter using TTL at the right hand side, which you can connect to. But when we use these as a building block, we shall not present either CMOS circuit or TTL circuit everywhere, because that will make it very complex. I mean, the whole circuit will look very complex. Instead of an inverter, depending on whether it is a CMOS technology or inverter or a TTL technology or any other technology, we shall put one symbol as a building block. We will know that inside, depending on the logic family that is used, one circuit or the other circuit will be there, okay? And that is represented through a symbol. The symbol over here you see is this one. So, this is the symbol that we shall be using for NOT gate. You may be already familiar with this, but to formalize this discussion, we put it over here. So, this is one way of representing inverting operation, okay? The other way of representing inverting operation is through Boolean expression. So, this is y is equal to a complement, okay, which is the which represents inverting operation, and it is represented through a bar or a prime. Both are equivalent. So, we shall use interchangeably these two notations. This can be represented through a truth table also. This is another representation. So, if you see a truth table which is like this, that is a low connected is associated with high, a high associated with low, 0 associated with 1, I mean at the input is associated with 1 at the output, and 1 is associated 1 at the input is associated with 0 at the output, we know that we are talking about inverting operation. There is an inverter circuit, if it is a digital circuit, there is an inverting operation that is involved. The fourth representation that we see is through timing diagram. And for timing diagram, we just look at one, before looking at the timing diagram, we look at one IC, which people use in the lab. You use TTL family because of issues with CMOS circuits, a lot of protections are required. So, mostly you will be using TTL circuits in the lab, TTL ICs. So, IC 7404 has got 6 NOT gates, and these 6 NOT gates are connected, the input and output pins are connected like this. So, and there is a VCC and there is a ground which is required, as power supply. Over here you have seen this power supply, this power supply. So, these power supplies are associated over here, and there are 6 such NOT gates inside it, okay. And if we give at the input of pin 1 a signal like which is low and high, 0 volt, 5 volt, it is just rectangular signal like this, then what will happen at the output? Whenever there is a low, there will be a corresponding high at the output. So, this is pin 1 and pin 2 that you see, okay, and that way it will continue, right. So, depending on how long these input signal is changed, you will see a corresponding timing diagram at the output. Now, all these things that we have discussed so far, these representations, in each of these it appears that the output is instantaneous. Like if you look at the Boolean expression or the truth table, you have given input, immediately you are getting output. That is the kind of understanding one may have from this kind of representation. But if you have timing diagram and if you expand the time scale, then you can have the propagation delay included in the timing diagram. Okay. So, depending on the time scale, right, if it is in the order of second or millisecond, you might not be able to visualize it. If it is in the order of microsecond or nanosecond, then you can see a nanosecond order of propagation delay involved. So, that way the propagation delay based representations are useful, and this propagation that we shall discuss and use later in some other discussion. Now, we look at representation of AND gate. Okay. So, AND gate, again, if you look at the circuit diagram, you will be having a circuit in the TTL space, which is which looks something like this. Okay. And remember, when we talk about design circuit of AND gate at circuit level, it is not a NAND gate, then again a NOT gate is put. So, in a NAND gate circuit itself, a inverting transistor block can be put, okay, with some associated additional circuitry, by which you can get NAND and NOT together AND operation. So, that is the Texas Instrument this data sheet. From that the circuit has been shown. This is a practical circuit which is in used for IC 7408. IC 7408 that uses this internal circuitry. Coming to the again, when we talk about AND gate and its use, then we will not be using the whole circuitry in various representations, rather its block. So, a 2 input AND gate, the block diagram, the symbol representation is like this, and 3 input it is like this. So, for 2 input, how this input and output in the Boolean representation would look like? It would look like this: y is equal to a and b, okay, and whatever this a and b you see, you can write in another manner b and a with whether the operator, if you just change the position, it does not make a difference. So, this is nothing but what is known as commutative. The operation is commutative. That means, the operands, if they change their order in the operation, there is no change in the output. So, this AND operation is commutative. Okay. So, this is another representation. So, IC 7408, this is the structure in which this is the arrangement in which 4 AND gates are there. VCC ground, and this 1, 2 is the input and 3 is the output. And if you send a signal, rectangular signal like this, in which the arrangement is such that there are these possibilities 0, 0, okay, then this is 0 and this is 1, this is 1 and this is 0, and this is 1 and this is 1. Okay. Then what do we expect? For AND logic, when both the inputs are 1, the output will be high. So, that is what you see for each of these cases. This is 0, 0, 0, this is 1. Okay. So, if you have a look at some such timing diagram, you can understand the circuit involved in between these two input and the corresponding output is nothing but an AND circuit, or AND logic is involved. Okay. So, it can be represented through truth table also. The way we had done, there will be 2 inputs and there will be one output, and when both the inputs are 1, corresponding output in the truth table will be 1, and for rest of the cases it will be 0. Okay. Now, what happens in this case when in the case of 3 input AND gate, we have similar such truth table. The kind of truth table that you can expect is like this. So, 3 inputs. So, there are 8 different possibilities, 2 to the power 3, 8 different possibilities of the input arrangement, and for each of these cases except when all the inputs are 1, okay, output is 0, right. So, that is what you see over here. So, that is the operation, and y is equal to ABC, right. And one important thing over here, if you first AND BC, right, which will generate an output 1 when both B and C are 1, and then this output you AND with A, right, then the output will be 1 when A is also 1. So, this is the case. So, BC is 1, just if you think of this is B and this is C, this output is fed to another AND gate. So, BC is 1 here as well as here, right, these two cases, but when A is 0, right, output is 0 because it is again getting ANDed, and when A is 1, output is 1. So, if you group BC, if you AND them together, right, and then AND with A, the output remains same as that of y is equal to ABC. And similarly, if you group A and B together and then you AND it with C, that means A and B, then this is ANDed with C, right, the result remains the same, the result remains the same. So, whether this grouping or association is done this way or the other way, result remains the same. So, AND operation is associative. Okay. Now, we look at OR operation. So, OR operation again the circuit, if you look at the circuit level, the circuit will be this is IC 7432, okay. That inside circuitry that is there, again you will see that it is not OR NOR gate which we discussed earlier and NOT gate which is put in succession or in cascade, rather within the NOR structure itself one inverting transistor is produced with associated circuitry with which you get OR operation, okay, that reduces the transistor count. Okay. So, again the whole circuitry we shall not be using for our subsequent discussions or developing more complex digital circuits, so we shall be using symbols. So, this 2 input OR gate symbol is like this, where A and B, the inputs that you see over here, if you just interchange the order or the operation the way you had done for AND operation, there is no change in the output. Okay. So, that is why this OR operation is commutative, right. And if you look at other representations like timing diagram, so for that if we use the IC 7432, IC 7432 is again a TTL IC which has got 4 OR gates inside it, and this 1, 2 is the input and 3 is the output. And similarly, if we look at 4 possible combinations at the input, the way the signal is presented to the input pins. So, you have got this 0 0 over here, 0 1 over here, 1 0 over here and 1 1 over here. So, for OR logic this is 0, and for you will see at the output of the pin, if you just look at the waveform, right, or the signal, you will see that the output is 1 when any of the input is 1. That is what OR logic is. Again, I have noted that before that if the time scale is expanded, which by which you can visualize nanosecond order time indices, then you can see the propagation delay involved in this timing diagram based representation. And of course, there is a truth table based representation where for B and C, for A and pin 1 and 2, okay, if they are any of them is 1, in the corresponding output in the truth table will be 1, and when both of them are 0, the output will be 0. Now, similar to AND gate, we can have multiple input OR gate also, multiple input OR gate, for which we just show an example of 3 input OR gate. So, this is the 3 input OR gate, and the corresponding logic diagram is any of the input 1, the output will be 1. Any of the input will be 1, output will be 1. That is what you see in this truth table, right? And similar to AND, OR is also associative. That means whether you group B and C first, you do B and C ORing first, and then you OR the output of this B and C with A. Whatever result you get, if you OR A and B, and then its output you OR with C, the result will be the same. I mean, what I had seen, what we discussed in case of AND gate. Okay, so similar thing is also applicable over here. So whatever is this, the same thing, instead of if you have got A and B, and then you are ORing with C, okay, the results remain the same. So this is associative. Okay. Now we come to NOR gate. Okay. So corresponding IC is 7402 in the TTL family. NOR gate circuit we have already seen before in earlier previous week, and for that we are using the symbol, the one that you see over here, this symbol. Okay. This symbol, we are not using a OR and then a NOT gate, rather we are putting this bubble over here. So this bubble whenever in relation to logic operation is present, you can consider that there is an inversion associated with that bubble. Okay. So put together it looks more compact. So this is your NOR gate, and the NOR gate truth table, we know it is just opposite of OR, right? Opposite, any of the input was 1 for OR, output was 1. Here any of the input 1, output will be then 0, right? And when both the input are 0, the output will be 1. Okay. So this is what you see for the OR gate. So I have not drawn timing diagram representation of this. So the similar thing can be drawn for the way we have done 4 possible combinations, and corresponding output can be drawn where both of them 0, the output will be 1. Okay. And note in 7402, it is this NOR gate IC, the 2, 3 is input and 1 is output. Unlike the previous cases, 1, 2 was input and 3 was output for AND gate and OR gate that we have seen before, right. So this is something for practical purposes you need to take note of. And Boolean expression, we just use this is OR and then a complement or a bar that represents the NOR operation. So this is the NOR operation in the Boolean expression of it. Now one thing is interesting over here is that whatever NOR operation you have seen, the kind of truth table that you have got, if you have the same inputs complemented and then ANDed, right, we get a equivalent representation. So let us consider this A and B, this is AND operation, right. So any of the input is 1, say this is 1, then this is 0, right. So that will make the output 0. A is 1, that means output is 0, right, because for the AND gate 0 is the forcing input. So 0 means output will be 0, right. So instead of that, if B is 1, this output will be 0, which will force the Y to be 0. Only when both of them are 0, so this is 1 and this is 1, this output is 1. So this is this case, this is nothing but NOR operation, right. So we can write this A plus B prime as A prime and B prime as well, okay. And we can see that this is also commutative, the way we have seen, and extending this one for more number of variables, okay. So instead of A, B, if you have got say C, D and all, then you can extend the same thing the way we had done for 2 variable cases, and we arrive at De Morgan's theorem, first theorem, which is saying, which is represented in this manner, okay. This is clear? Now we look at NAND operation, okay. So NAND operation is similar, again the way we had discussed NOR, we are not having a two different symbols, that is and not put together. Rather, we are putting one single logic gate with bubble means and, then there is a inversion associated. Okay, and the corresponding truth table is output is 1 when any of the input is 0. Any of the input is 0 for AND, output is 0. So, in this case any of the input is 0, output is 1, and only when both the inputs are 1, the output will be 0. Okay, and the corresponding the IC that we use in the TTL family is 7400. So, 1, 2 is the input and 3 is the output. So, 4 such these gates are there inside the IC, and we can have a corresponding timing diagram. Okay. And for NAND gate, what we had seen in case of NOR gate, a similar thing occurs over here. While the NAND representation, this AB, this is the Boolean representation complemented, that is what is the NAND operation over here. The same thing we can obtain where the inputs are complemented and then ORed. Okay. So, A bar plus B bar, how is it done? So, just you consider any of the input as 0, this is symmetric, so it will do. So, then this output is 1. For OR gate, 1 is the forcing input. So, if the OR gate input is 1, the output will be 1, right. So, that is what is happening over here, and if you extend it to more number of variable like A, B, C over here, right. So, then the corresponding expanded version in this form will be A bar plus B bar plus C bar, right, and so on and so forth. So, that is giving you De Morgan's second theorem, which is also very useful, which we shall discuss more later on. Okay. Now, universality of NOR or NAND gate, this is something interesting. This is useful in the sense, if you have only one, if you think of only one variety of gate by which you would like to get many different logic operations or Boolean expression realization of that, then you have to pick up either of NOR or NAND, okay, because they can be converted to any other logic operation by different combinations of themselves. So, that is the good thing about it. So, you can have only one variety of it, one kind of fabrication process which is useful. Otherwise, for AND gate and OR gate or different variety, there are different kind of circuitry that we have seen before. So, NAND you just having only one kind of circuitry. And how you can achieve it? So, we just give some examples of basic Boolean operations. So, from NOR gate, if you want to get a NOT operation, right. So, you just need to short both the inputs and then the corresponding output will be the invert of this. I mean, if you remember the NOR logic, so this is A, B and Y. So, when 0, 0, 0, 1, 1, 1 and 1, 0 and 1, 1. Okay. So, NOR logic, any of the input is 1, output is 0, right, and when both the input are 1, output is 1, right. So, if you just short both of them A and B, so common one, then what is happening at that time? So, either 0, 0 case is there or 1, 1 case is there. When 0, 0 is there, output is 1, and 1, 1, output is 0, just opposite of it, right. The other thing for NOR gate, we know 0 is the non-forcing input, right. So, if you have a NOR gate, right, so which is you connect to 0 and this you connect to A, how the output will be behaving, right. So, B is 0, so this is the case and this is the case, these are the two cases, right. And at that time, if A is 0, output is 1, if A is 1, output is 0. So, that is also giving you an inversion, is not it, right. So, that is the two ways you can get NOT operation from a NOR gate, two input NOR gate, okay. And how you can get OR operation. So, NOR and followed by a NOR followed by NOT, you get OR operation, right, just inversion of So, this was A plus B bar. Okay. So, this is A plus B bar and again another B bar. So, it will get A plus B, clear. And how you get AND operation? Earlier we have seen y is equal to A plus B bar is A bar B bar, right. So, if at the input if you send complemented A and complemented B, then you get A and B. Okay. So, that is the that is how we are getting AND operation over here, clear. So, similar thing would happen in case of NAND gate also. You can get any other operation like AND, inversion. For inversion in this case, right, what is the other? So, this is one option, that is, this is one option we have already noted over here, right. The other option is non-forcing input for NAND gate is 1, right. So, if you give this as A and this is the corresponding output will be. So, this is, if this is 0, 0 1 output will be 1, right. If it is 1 1 1 output will be 0, right. So, you get the inversion for some such arrangement as well, right. And AND operation is NAND followed by NOT, and OR operation again we follow the De Morgan's theorem, right. Y is equal to AB prime is equal to A prime plus B prime. So, if you send primed version of it, complemented version of it, you get OR operation. Okay, clear? So, the last topic that we discuss in this lecture is the usefulness of AND or invert gate. Okay. So, when we realize Boolean expression, we shall discuss it in future classes. So, there could be many different cases where you are having relationship like AB plus CD plus EF, right, inverted kind of thing. So, basically there is a AND operation involved, this is AND, then this is OR, and then finally an inversion is taking place. Okay. So, this is called AND or invert. So, if you want to realize these separately, right, the number of transistors involved will be as it is required for each of these realization. But within the logic family there are gates or the arrangements can be made by which this AND or invert operation can be done with lesser number of transistors. So, for CMOS it is very easy. You can see that this is an example of 2-1 AND or invert gate. So, these are the two inputs, these are the two inputs over here, and so that's this is the 2 and this is the corresponding 1 input. So, these two are ANDed, B and C are ANDed, and this is ORed with A, and corresponding these are the NMOS side and these are the corresponding PMOS side where B and C are in parallel, these are in series. Here in NMOS side it is series, PMOS side it is in parallel, and A will be in this side is in parallel because of the OR operation, and in this side this is in series. Okay, that we already know how we get CMOS circuits. So, very convenient way of getting it, and we can get OR and invert gate also in similar manner for in CMOS circuitry. Okay. TTL family also has similar such gates and or input gates. So, one example is 7451 which is dual, that means two such gates is there, one and another. Two input, that means these are the two inputs that you see, two inputs, two wide means two such blocks are there, right, by which you can get AND or invert gates, and this is the corresponding circuitry in the TTL family from the TTL data sheet. And you can have expanders also arrangement by which more such gates can be added and more complex circuits can be arrived at. Okay. This saves in a transistor count. Okay. So, these are some basic gates which are useful in realization in practical circuits or in your laboratory experiments which you will be undertaking, or And so, to conclude, the logic circuit operation can be represented by symbol, Boolean expression, truth table, timing diagram. We have seen that. AND or NAND NOR operations are commutative, but AND OR operations are associative. The corresponding NAND NOR are not associative, which we shall discuss more later on. NOR operation is equivalent to ANDing of complemented inputs, De Morgan's theorem we have seen one version. NAND operation is equivalent to ORing of complemented inputs, another De Morgan's theorem. Any other logic gate or operation can be obtained using only NAND or NOR gates, which is universality of these two gates. And AND or invert gate takes less number of transistors in comparison to implementing them separately, which is useful in many cases. Okay. Thank you.